My dear students, we were discussing about evenness. So already we have discussed about the evenness, definition of evenness in textile materials, types of irregularity, which is defined by weight per unit length, the irregularity in diameter, irregularity in twist, irregularity in strength, and hairiness. So we have already discussed about index of irregularity. So definition of index of irregularity. We have discussed about U percentage, which is also called percentage mean deviation, and the relationship between the coefficient of variation and percentage mean deviation. Then we have discussed about various types of variations. They are random variations and periodic variations. Periodic variations are classified as short term, medium term, and long term variations. We already have discussed about this type of variations. Now, addition of irregularity. The variance is having the additive property. So the variance or the coefficient of variation can be added together when we will try to combine different material of different value of coefficient of variation or the variance. Now effect of doubling will cause the reduction in the irregularity. So as the doubling will be increased, the irregularity in the textile strand will decrease. So that is based on this formula as shown here. CV of double strand will be equal to CV of individual strand divided by under root n. N is the number of doubling. Here the value of n is 2. Now limit irregularity, already we have discussed about the definition of limit irregularity, its numerical expression, and index of irregularity I. Already we have discussed about. So now we will proceed further. Now come to the variance length curve. So variance length curve is nothing but the effect of length of the specimen on the variance of the specimen. So that is called variance length curve. So as you can see here in this diagram, the yards, that is the length of the yarn for example, and yarn thickness. So yarn thickness, if it will be measured, yarn thickness or yarn diameter across the length of the yarn, you will see there will be increment and decrement of yarn diameter. So yarn diameter will vary with the length. So this is a variance length curve. So now if you talk about the variance, mass variation of the yarn, so total mass variation, that will be expressed by Vt, T for the total variance. So total variance can be classified or divided into two type of variation. One type of variation is called as variation between the length, and another type of variation is called variation within the length. So what is the variation between the length? So for example, we have a total length of specimen, say capital L. Now we will just cut the total length of capital L to small l amount. So now we have made the yarn specimen of small l of n numbers, for example. Now we will take the weight of each and every L length of the yarn specimen, and then we will calculate the mean mass, as well as we can be able to calculate the mean standard deviation and variance. this variation is called variance, as well as we can also calculate coefficient of variance, CV percentage. So that CV percentage is called variation between the L, that is expressed as CBL, small l, that is the variation between the length, and corresponding variance that is symbolized as BL. When we are expressing CBL, that means it is the coefficient of variation, coefficient of mass variation between the length, and when it is expressed as BL, then it is the variance of mass variation of individual L length. Right? Now next concept, that is the variance within the length. So now we have the cut length of L, small l amount of length of yarn. Now if you are going to measure the mass variation within that L length of yarn, only we have the L length of the yarn now. Now we need to measure the mass variation within that L length of the yarn only, small l, that L is small l, length of yarn only. And if you measure that, the mass variation of each individual length L, then the CV percentage of that mass variation of L yard length is symbolized as CBL, and the variance is expressed as VL. Right? So that is called variation within the length. Now total variation VT, that will be the summation of variance between the length, that is BL, and variance within the length, VL. Okay, so BL and VL, so if you will add together, then that will come out the total variance VT. Okay, now here you can see this red line curve. Here the yarn length versus BL, that is the between the length, has been plotted. So you will see at the zero length of yarn, the variance between the length will be maximum, but as the length of the cut length of the yarn is increasing, that variation between the length is gradually decreasing. So when there will be the shorter length of cut length, okay, say 1 millimeter length you have cut, and you have measured the mass of each 1 millimeter length of the yarn, and you calculated the CV percentage and variations of those mass values, then you will see the maximum value will be in case of 1 millimeter cut length. If you are going to increase the cut length, for example 10 mm, 100 mm, 1000 mm, then you will see that variation between the length will go decreasing, the decremental trend as shown here in this red line. And in case of variation within the length, the next graph, bottom one, you will see as the cut length is increasing, in the zero cut length, the variation within the length is zero, minimum zero. But as soon as the cut length is increasing gradually, the variation within the length is gradually increasing, and at a maximum cut length or total cut length, the variation will be maximum, that will touch the total value, VT value, that will be maximum. Right? So it's a mirror image. Basically the BL curve and VL curve, they are actually mirror image of each other, and the upper line, that is the VT line, that is the total variance line. So these two curves are called variance length curve. These two curves are very important for analysis of the variation in textile specimen. Now come to the causes of irregularity. What are the various reasons of irregularity in textile material? Irregularity caused by raw materials. Natural fibers have various varieties. They have no true fixed length, fineness, shape of cross section, maturity, crimp, etc. in case of natural fiber. So each and every such properties or qualities of the natural fiber are having variation. So which can affect the yarn properties and especially evenness. So if your raw material is uneven in nature, so your end product, that is yarn, fabric, they will be also uneven. So these variations are due to different rate of cell development due to changes in the environmental condition. During the cultivation of the natural fiber, due to the variation in nutrients, soil, weather conditions, such variations always will be there. In man-made fiber, variation in mass per unit length occurs due to changes in polymer viscosity. During the melt spinning of the melt spinning or solution of the man-made fiber, so there may be changes during the polymer viscosity due to the changes in temperature, some other chemical ingredient. So that will be the cause of variation in the linear density. Then roughness of the spinneret orifice. So if the spinneret orifice is smooth, then that will produce smoother fiber with less variation. But if the spinneret orifice is rough, so that will also produce the rough fiber. Surface roughness will be there, variation will be there. Variation in extrusion pressure. If the extrusion pressure in the filament production will vary, then the rate of extrusion will change, then thick and thin filaments will be produced as per the changing pressure. Filament take up speed. If take up speed will vary, when the take up speed will be faster, filament will be finer. If the take up speed will be slower, then filament will be coarser. There will be variation. Presence of delusterant or additive. If you add some delusterant, suppose titanium dioxide, or some additives, anti-static finish, flame retardant finish, different color, so then that will also affect the mass variation of the fiber because of the amount of delusterant you are adding or additives you are adding. They are not in equal manner you are adding. You are maybe adding that additives in different concentration in different time. So then there will be the variation. So which can modify the particular shape and fiber surface geometry. So these are the causes of irregularity in case of natural and synthetic or man-made fibers. Now come to the next point. Number 2, irregularity caused by fiber arrangement. So textile fibers are not rigid in nature, they are flexible. Their manipulation during conversion to yarn is an immensely complex combination of mechanical movement which usually requires some degree of compromise. So basically textile fibers are not rigid, they are flexible. So now we are imparting twist to the textile fiber. Now textile fiber will behave differently in different machine condition. There are many factors will affect. All textile fibers will not behave in a same way or similar way. They may behave in different way depending upon their flexibility and accessibility of the machine surface. So that will cause some variation during that manipulation of the fiber for formation of the yarn. So the desirable result of relocating large number of fibers at a high speed and arranging in well order form tend to be difficult. So it's difficult to arrange all those fibers to make a different fiber strand. Suppose you are producing sliver from the lab in a carding machine. So it's difficult. It's not an easy task to relocate large number of fibers in a concise manner or in an even manner or in a typically well organized manner inside a sliver. So that's why there will be variation. Fibers assemble into form of twisted strand constitute a yarn. So if the twisting is not uniform, and fibers are not responding well during the twisting operation, then there will be the ununiform strand produced during the spinning operation that will cause variation. So fibers are not precisely laid end to end. The gaps are present between the fiber. So not all fibers are connected to each other at end to end. There will be the distance or gap between the two fibers when they are laid inside a textile strand, such as yarn. In case of yarn or sliver or roving, always there will be a certain gap between the two fibers. As a result of yarn twist, fiber arranged in spiral form in a series of folds, kings and doublings. So all those, that the gaps between the fibers, that series of fold, kings and doublings which were there during the spinning operation, so all those are the source of irregularity in the fiber strand. Now third point, effect of fiber behavior. Fiber shape directly affects yarn irregularity. Shape of the fiber cross section, that is the shape, arrangement of the fiber section and space between the fiber will vary from yarn section to section. Hence, the mass of each section will differ. So fiber cross-sectional shape is not also uniform, and that organization of the fiber of different cross-sectional shape is very difficult to predict, and due to that there will be the variation. Then number 4 point, inherent shortcoming of the machinery. Sometimes the machinery itself is having some shortcomings, and machines are difficult to apply uniform action to all textile fibers or textile materials to obtain the uniformity. In spinning, it is surprising how often the individual fibers are only negatively controlled. At times, they are carried forward by air currents or jostled along by the surrounding fibers, or they are held in position by friction and twist. The fiber manipulation by rollers, aprons, gills, and other machine parts is hampered by fiber variation, and the machines can only be said to give the best result within the limitations imposed by the material. The drafting wave is one of the examples of irregularity due to the inability of a drafting system to control each fiber. So each fiber cannot be controlled by the machine parts. They are called floating fiber sometimes. So those floating fibers which are not directly in control of the textile machinery or machine surface or machine parts, suppose rollers or aprons, they will cause irregularity, which is one of the example of that kind of irregularity is called drafting wave, that you must heard about. Whether roller drafting is used, the distance from one nib to the other is greater than the length of the shorter fiber. The shorter fiber, that's why, will be out of control and they will produce irregularity in terms of drafting wave. The short fibers float in the drafting zone and move forward in an irregular but cylindrical manner. Cyclical manner, and which result in drafted strand having thick and thick places in a wave form. So the wavelength of this type of irregularity is about 2 to 5 times the mean fiber length, but it is not necessarily constant for a particular strand. In addition to varying wavelength, the amplitude of the drafting wave is also variable. Amplitude means that in the diameter direction, the diameter of the fiber, that is the amplitude, that also will vary. So the wavelength is basically the lengthwise variation at the lengthwise direction. Okay, how long the thick place is continuing, that is the wavelength, and how much thick place is it in the diameter direction, that is the amplitude. Now next point, point 5, mechanically defective machinery. Sometimes machine parts is defective. The machine drift out of the adjustment bearing, become worn, components get damaged, and lubrication system clogged, and dirt works its way into the mechanism. So sometimes some machine, due to the faulty operation of the machine parts, there will be the faulty or unirregular or irregular textile material such as sliver, roving or yarn produced. The faulty roller, top roller eccentricity is one of the uh, serious fault sometimes or seldom occurs in the textile machineries. Eccentricity of the top roller and gear wheel gradually produce periodic variations. Now, importance of yarn evenness. Why we are talking about yarn evenness? How it is important to understand. The most obvious consequence of yarn unevenness is the variation of strength along the yarn. So, if the yarn will be uneven in nature, that means the yarn is having mass variation in the mass, then that will cause the variation in the strength of the yarn. So, when there will be the strength variation in the strength of the yarn, so there will be the weak places in the yarn. So yarn always will break from the weak places because the weakest point of the material is the strength of the material. The strength of the weakest point of the material is actually the strength of the material. And when there will be the mass variation and during the application of the twist for the spinning operation, the the fine part of the yarn will be highly twisted and they become much finer due to the compaction. Okay, so because the twist always try to migrate to the thin places. So the thin places will be highly twisted, the thin places become much thinner, more thinner, and thick places, in case of thick places, the twist migration will be less and thick places will be appearing much thicker. This is one of the consequence of the yarn unevenness. Then a second quality related effect of uneven yarn is the presence of visible faults on the surface of the fabric. So if there will be the uneven yarn is having thick places, thin places and naps. So all those faults will be also present on the surface of the fabric and that will hamper the look of the fabric, aesthetic appeal of the fabric. Then the next point, the problem is particularly serious when a fault, thick or thin place, appears at precisely regular interval along the length of the yarn. Sometimes there are periodic faults in the yarn, and due to that periodic fault, the same fault is coming again and again at the same place, and that will create a band over the fabric. Okay, they are called as bar, diamond bar, or different type of bar will come like a band of thick place or thin place, alternation of thick place and thin place. There is a serious fault. In such cases, fabric construction geometry ensures that the fault will be located in a pattern that is very clearly apparent to the eye, and defects such as streaks, stripes, bari, or other visual grouping develop in the cloth. So these are the such kind of defects in fabric when they are with the periodic variation in the yarn. They are called as streaks, stripes, bari, depending upon the type, the visual appearance of that periodic variation in the yarn. The twists tend to be higher at the thin places in a yarn. Thus, at such location, the penetration of dye or finish is likely to be lower at the thick region than at the thick region of the lower twist, which means due to the higher twist in the thin places, the absorption of the dye will be lesser in the thin places and the absorption of the dye will be much better in the thick places. So thick places will be dyed with the darker shade and the thin places will be dyed with the lighter shade, and that as a result there will be the shade variation depending upon the thick places and thin places in the fabric. That will also cause a serious defect. Other fabric properties such as abrasion or peel resistance, soil retention property, drape, absorbency, reflectance, luster, So all those properties are also directly influenced by the yarn evenness. So if the yarn will be uneven, there will be the irregularity, mass irregularity in the yarn. So all those problems will be coming. So these are the significance of the yarn unevenness in textile science. Now effects of irregularity. What are the effects of irregularity? The strength already I have discussed. The thin places in sliver, roving or yarn will be weak places, because in the thin places there will be the less number of yarn. Always the thin place will be the weak place, and the greater will be the chance of breakage of the more irregular yarn. Then fabric appearance. The fabric appearance will be hampered when there will be the periodic variation in the yarn. So due to the periodic variation in the yarn, various kind of streaky or patchy fabric will be produced. That already I have discussed. In warp, it gives streaky appearance. In weft, diamond bar and block bars can arise. Okay, so that they are depending. These type of defects are there depending upon the shape and dimension and appearance of that defects over the fabric. The condition of diamond bar. How the diamond bar are produced. W equal to R plus X into lambda, where lambda is the wavelength of the periodic variation in the yarn. So after how much length the same defect is repeating, that is the lambda. R is the integral multiple of half, and X is the value less than, it's a constant, its value is less than 0.25. This means to cause a diamond bar, a weft must have a periodic variation whose wavelength is less than the twice the fabric width. Okay, so if there is a periodic variation in the yarn, for example, a thick place in the yarn, and that wavelength of that thick place is less than the twice of the fabric width, then the diamond bar will be produced surely on the fabric. This is a condition. So that has been this type of concept has been there. So students should learn this formula, how the diamond bar has been produced in which condition. Dyeing faults. One effect of yarn irregularity on the dyeing process is the thicker and softer part of the yarn take up more size than the thinner and harder region. So size, during the sizing operation also, the thick places they will absorb the more dye and more size, and the thinner places they will absorb the less size. So after desizing process prior to dyeing, the distribution of the residual size may be uneven and cause difficulty in achieving the level of dyeing. Okay, so when the size uptake will be different by the thick places and thin places, then in the desizing operation, maybe thin places will be easily desized but thick places will not. So that will cause the uneven dyeing. Yarn breakage. Processability of the material is affected by yarn irregularity. Processing means mechanical processing. If there will be the yarn irregularity, thin places will be there. So thin places are the weak places. The yarns will be broken. Or if the fabric is having, or the yarn is having naps, the naps are having the much higher diameter. So when the yarn will be passed through heel dye or reed during weaving, it will create problem and the yarn will be broken. The method of measuring yarn evenness. What are the methods? There are various types of methods available for measurement of the yarn evenness. I shall discuss one by one. So first one is visual examination method. So in this method, basically we need to use one blackboard, a drum, a photographic device, projectors and a lap meter. So here in this type of method, so we will wrap the textile strand over a blackboard, and then after wrapping we will see visually how many uneven places are there, how many thick places, thin places and naps are there in case of yarn. So if it is a even yarn, there is no such kind of defects, then on the blackboard the appearance of the yarn will be very even, right? Then we will compare that blackboard with some standard yarn board, and based on that appearance we'll give some grading 1 to 5. For example, 1 is the highest grading, there is no uneven places, thick place, thin place or naps on the surface, and 2 is the higher unevenness, 3 is the more higher unevenness. In this way we can grade. That is a visual examination method. It's an easy method. In industry, these visual examination methods are practiced in case of yarn spinning mills for to identify the thick places and thin places in the yarn surface. Then cutting and weighing method. So here, in case of textile strand which are much thicker in nature, such as lap, sliver, roving, even in case of yarn also, so basically we will cut the yarn in different length, and then we will take the weight, and then by taking a number of samples, the weight of number of samples, then we will calculate the average weight, standard deviation, variance, CV percentage. So then we will go for the plotting of the variance length curve, which we have already discussed. So that is possible by the cutting and weighing method. Then next point is electronic capacitance tester. So here one capacitor will be used in the instrument. There will be a capacitor. So in the capacitor there will be the two parallel plate. So within these two parallel plate there will be the dielectric medium. So when there will be no presence of the yarn in between that two parallel plate, the parallel plate capacitor will show some capacitance value. But as soon as the yarn will be present between the parallel plate, then based on the mass of the yarn, the capacitance of the capacitor will change. So that change in capacitance will be measured by the instrument continuously. So yarn will be passed continuously across these two parallel plate capacitors, and the variation in the mass variation of the yarn will be measured in terms of the change in capacitance value. So that is the electronic capacitance tester. So it's an electronic instrument, one kind of latest technique which is available now in industry. Then variations in thickness under compression. This is another mechanical type of tester where the textile strain will be passed through one groove and tongue type of roller. In the groove type of roller, textile strand will be passed and the tongue will be resting over the textile strand. And whenever there will be the variation in the mass, the tongue lever or tongue roller, that will having some upward and downward movement based on the thickness and thin places of the textile strand. So based on the movement of the tongue roller over the textile strand, so one can measure the thickness of the textile strand and thickness variation of the textile strand. So that is the thickness under compression. That type of instrument has been developed by WIRA. And in case of roving, that instrument is called as WIRA roving evenness tester, and LINRA roller yarn diameter tester for the yarn. Now photoelectric tester. So WIRA photoelectric testers and LINRA photoelectric testers are available, where there will be some photoelectric principle. That photoelectric principle is used for measurement of variation of thickness of the yarn. So there will be some mirrors, and based on that mirrors, the change in thickness of the specimen will be measured. So that will be discussed in detail later on. Now miscellaneous method, other than there are airflow method, mercury displacement methods, they are also proposed by some researchers. So before actually going to the method in detail, it must be kept in mind that most important property of a yarn is the number of fibers in the cross section, and variation of this number along the length is a fundamental measure of irregularity. So this is the basic concept of irregularity. if the number of number of fibers in the yarn cross section is constant throughout the length of the yarn, then there will be the evenness of the yarn. But as soon as there will be the changes of the number of fiber across the yarn cross section, so there will be the unevenness. Now visual examination method. So yarn appearance board. So here you can see the yarn appearance board. So yarns are wrapped over the board, and the grading has been given: grade A, grade B, grade C, and grade D. So these are the standard yarn appearance board. So you can see in case of grade A, there is no thick press, thin press, very rare. Thick press and thin press and naps are available. In case of grade B, a more thick thin presses are there. In case of C, you can see there are little more higher thick press, thin press, and naps are there. In case of grade D, a large number of thick press, thin press are there. So you need to wrap your yarn over that board. There are particular rules available, so that is written in the previous slide that you can go through. So based on that rule, if you follow, you will prepare that board, black on a black board, and then you need to compare your yarn quality, which will be matching with these 4 grades. So as per that, you will decide your grade of the yarn. Okay, so sometimes the yarn is having some repeating fault or periodic fault. So due to the presence of that periodic fault, you will see the same defect is repeating at the same position again and again. So now you will only watching at one surface of the board, not the back side. You are seeing or watching the front side of the board. So in that case, you never can see the periodic fault if the fault is hidden at the behind the back of the board. Okay, so in that case, you need to use the tapered board. Okay, so the board should not be in a particular rectangular form. The board should be tapered board. That means its two side will not be same. So in that case, when you will use tapered board, just you can see here in this diagram, the length of this side is higher than the length of this side, right side. So in that case, in such kind of tapered board, when you will wrap the yarn, if there is a periodic fault, so once upon a time that fault will be come at the front surface, and that the fault will be appearing like this angular line. So that will give you the information about the periodic fault which is there present in the yarn, right? So this is the reason why tapered boards are used to identify or to catch the periodic faults present in the yarn. So ASTM standard test method describes the yarn appearance into 5 grades as I have shown in the last slide. The board is compared with the standard photographs and then graded. The grade A, grade B, grade C, and grade D, and they are given in the last slide. Now grade E, that is the below the grade D, and more defects are overall rougher appearance than the grade D, right? So grade D, that is not given in the previous slide, but grade E is also there, that is the worse than grade D. Gravimetric method is another method where cutting and weighing method. You need to cut the sample in a particular length. Suppose in case of lap meter, when you are going to measure the uniformity of the lap, automatically unroll the lap, break off 1 yard length. So 1 yard length cut will be there, and deposit into the pan of a scale for the measurement of the weight, whether the recorded subsequently. So data analysis. So in the lap meter, the lap meter will automatically cut off the 1 yard length of the lap, and that will be weighed automatically, and a number of samples, suppose n number of such 1 yard length of the lap samples will be measured. Their weight data will be coming, and the standard deviation, coefficient of variation, and the variance will be calculated, and based on that you can produce the BL curve, the variation between the length curve. Then come to the sliver, robbing and yarn. So the cutting and weighing method similarly, but length will be varying. In case of sliver, the length will be normally 6 yard. Then the 6 yard length will be measured by a wrap block. In case of robbing, 15 yard length of the robbing will be cut, and that is also measured by the wrap block. And in case of yarn, 120 yard lee will be prepared. That is actually measured by wrap reel. The wrap reel you already know, you have seen in the laboratory. So these are the uh, gravimetric method. Then now the next method, by measuring the variation in thickness under compression. So that is in case of WIRA robbing levelness tester is there for the compression method, as well as yarn testing is also there in the same method. So here you can see the device for the robbing or the sliver levelness tester. Here there is a groove and tongue type of roller. The bottom one is the groove roller, top roller is the tongue type of roller. So in between these two roller, the textile strand, that is the sliver or robbing, is fed. Okay, so when there is a variation in the robbing, that tongue roller, which is the top roller, that is having deflection. So that deflection will be traced over a graph paper. So here that graph paper is shown, the deflection has been traced. Whenever there will be no variation, then there will be no deflection of the tongue roller, and the line will be perfectly straight line. This line on the graph paper will be perfectly straight line. But as soon as there will be some deflection, there will be some variation, zigzag lines will be there. That will be the measure of the variation in the thickness of the textile strand. So based on that trace on the graph paper, one can calculate the mean diameter, and as well as the standard deviation, coefficient of variation of the textile strand. Now yarn testing by compression method. So here you can see this diagram. So here actually two diagrams are shown, A and B. So A is called Anderson yarn tester and B is called the Linra roller yarn diameter. So in case of A, there will be the anvil and there will be the shoe. The shoe is resting over the fabric surface. Shoe is basically resting over the anvil, and the yarn or fabric that will be placed over the anvil. Okay, now the shoe will be resting over the yarn or fabric, and the yarn will be drawn gradually. So whenever there will be the thickness variation in the yarn, the shoe will having some deflection. Okay, at the same lever of the shoe, there will be one mirror attached, and over the mirror, one light ray, a beam of light is actually reflected through this mirror. So whenever there will be no deflection, no irregularity on the yarn surface, then there will be no deflection of the yarn. So no deflection of the shoe, and there will be no deflection of the light ray which is reflected by the mirror. But as soon as there will be little change in diameter of the yarn, there will be the little movement of the shoe, and then that light ray which was reflected from the mirror, that also will be deviating. So the instrument will measure that deflection, and that will be the measurement of the yarn unevenness. And in case of B, you will see there are group of rollers, vertical rollers, 1, 2, 3, 4 and 5 rollers, and there are two red rollers. Now yarn is fed to this roller, red roller top one, then it will be wrapped over these surfaces, and then again it will be coming out of that bottom red rollers. Okay, now the yarn is wrapped over these three rollers. Now yarn is passed in these rollers. When there will be the evenness in the yarn, there is no thickness variation of the yarn, then the anvil which is resting over the top roller, the anvil is not having any deflection, so the micrometer will not detect any deflection, there is no variation. But as soon as there will be the variation in the yarn, the small variation in the yarn diameter will be causing the deflection to the anvil. So anvil is having some vertical movement, and that small, very small vertical movement will be detected by that micrometer, and that will be the variation in the diameter of the yarn. Now electronic capacitance method, this is available in case of Uster. Uster is one of the machine manufacturer and very famous for measurement of ion unevenness. So indirect method, this method is indirect method of measuring the change in mass per unit length of the ion. The ion is passed through a parallel plate condenser in a continuous fashion. Okay, we will see this red condenser, parallel plate condenser or capacitor. The ion is passed across these two parallel plate capacitor. A change in mass of the dielectric or non-conducting material, that is the ion, in the condenser changes its capacitance. The unit length being the length of the capacitor. The length of the capacitor is the unit length of the ion. That is, for in case of Zellweger Uster, that is the 8 millimeter. That is the length of this capacitor or length of the ion which will be inside the capacitor. The change in capacitance will follow the variation in the weight per unit length, the length of the capacitor of the material, right? The change in capacity is translated electronically into a meter reading which indicates the CV. So basically the instrument will give a signal in terms of change in capacitance value. Now there is a conversion of the capacitance to the ion CV percentage, mass variation percentage. Okay, that is done by the instrument. That's why it is called indirect type of tester. So the instrument will measure the capacitance. That capacitance value will be then again processed to change it in mass variation. So this is the Uster principle of the Uster tester. So this Uster tester is one of the famous tester and most widely used testing principle in textile industry. So the Uster tester will produce this kind of graph. Okay, now if you read this graph, you can be able to measure the U percentage by this formula, A by X into T, where X is the distance, okay, and X bar is the X bar distance, and this is the individual X distance, and T is the total length of the yarn, and A is the actually the amplitude, okay, from the average value how much deviation is there. The CV percentage will be equal to sigma by X bar, okay, where sigma bar can be written as 1 by T, that is the length, integral of x minus x bar ka whole square dt. So x minus x bar, that is the deviation. So when we are taking the integration, that is the total deviation, and when we are dividing by dt and it will integrate it, that will be the mean deviation. So this is the formula of CV percentage. So by using this formula you can be able to calculate the CV percentage from this graph. So here the Uster U percentage for carded cotton yarns are shown. The 20s count carded cotton yarn is having the values of 12, U percentage 12, that means the yarn quality is good. In case of 30s count, the 12.5, then yarn quality is good. In case of 80s count, the 16 will be the U percentage, then the yarn to be considered good. Okay, so larger deviation from the mean in case of CV percentage as it is squaring. So CV percentage values have greater impact on yarn appearance and their processing behavior. So CV percentage is a better measure of the unevenness than U percentage. That already I discussed in the class, why CV percentage is better than the U percentage. Okay, now associated Uster equipment that I shall discuss in the next lecture. Thanks for the listening. Hope you enjoy my voice.